Very good morning, students. This is class 3. So, in class 3, we are going to discuss about what are different types of fluids and what are properties of fluids here. So, previous class we have seen what are different types of properties of the fluid, what is density, what is specific weight, what is specific volume, what is specific gravity. Then we have seen what is viscosity, then kinematic viscosity, then Newton's law of viscosity. Then we have seen different relations of different properties of the fluid. So in this class we are going to discuss about what is fluid and types of fluid and properties of the fluid here. Fine. Now already we know what is fluid, a substance of capable of flowing or which undergoes deformation under the influence of stress. Okay, or there are two types of fluids will be there. One is liquid and one is gaseous. Liquid where it takes the shape of the container, whereas gaseous, okay, it does not take the shape of the container, but it will try to expand its volume throughout the container. Okay, in liquids we have seen what there is no there is a free surface will be formed in case of liquids, and whereas in gases there is no free surface. Then examples of fluid: water, milk, kerosene, petrol, emulsions, etc. Then what are types of fluids here? There are different types of fluids are there here. One is ideal fluid, one is real fluid, and one is pseudoplastic fluid, Newtonian fluid, and non-Newtonian fluid here. We shall discuss one by one here. Then what is ideal fluid? An ideal fluid is a fluid that has no viscosity. As we have seen in like Carnot cycle. Example, if I take Carnot cycle it is an what? 100% efficiency engine. Yes? Then we have seen if it is an 100% efficiency, there is no such engines that does not exist 100% efficiency. Okay, like that, ideal fluid is one in which there is no viscosity. Okay. Then compared to ideal fluid, we are comparing other fluids here. So ideal fluid to other fluids we are trying to compare. Like how we are comparing Carnot cycle to other cycles, like that we are going to compare the ideal fluid to other fluids here. So therefore, ideal fluid is one in which whereas exactly there is no viscosity. Fluid does not have viscosity. It is incompressible. But practically, as that of Carnot cycle, here in ideal fluid also, there is no such fluid exist here. Fine? I think the concept is clear. That is what ideal fluid it says. Okay? If you see the figure, okay, then the fluid that is flowing through a pipe, okay, flow of an ideal fluid. If you see this, okay, the top figure, if you see flow of an ideal fluid, okay, but there is no such fluid which flows like this. Okay, but second figure, if you see, the fluid goes on variation. Okay, flow of viscosity, how exactly you can see here. Okay, the flow of viscosity goes on changes, but in above figure, the flow of viscosity is continuous, but there is no such the fluid. Okay, where exactly the viscosity is constant, but viscosity goes on changes. That is what it can be called as ideal fluid here. Fine. So ideal fluid, it is having no viscosity, it is incompressible in nature. Okay. So practically no ideal fluid exists. Then what is real fluid? So real fluid are compressible. Okay, that's what we can call as real fluid. Example, your like Joule cycle or like petrol engines. Okay, so those are called as something about real engines. Compared to real engines, we are comparing to Carnot cycle here. Okay, so real fluids are compressible in nature. They have some viscosity, and real fluids implies friction effects. But in ideal fluid, there is no friction because no viscosity means no friction. Because here there is a viscosity, friction will take place here. Example, kerosene, petrol, castor oil, etc. Here you can see this pipe. Simple example: velocity distribution of pipe in a flow. Okay, so there is like round portion. If you are seeing it is a pipe, the fluid is flowing. What is ideal fluid and real fluid? It says the ideal fluid is continuous. Okay, you can see the profile. Ideal fluid is continuous lines are there, but whereas here something about the changes in variation of the fluid here. Okay, much variation is there regarding real flow and ideal flow here. So that is what the difference between you need to understand what is ideal fluid and real fluid here. Okay. Then after knowing what is this ideal fluid and real fluid, let us understand. So what is pseudoplastic fluid or what is ideal plastic fluid? Pseudo means otherwise it can be called as ideal. Okay, a fluid whose apparent viscosity or consistently decreases. Okay, viscosity what happens? Okay, so consistently decreases instantly with increase in shear rate. Okay, so what happens when I apply a shear rate or shear stress on this fluid? What happens? Apparently, the viscosity goes on decreases. Okay. Example: what happens? Suppose, for example, if you apply a stress on the sand, if you go to any beach areas or any when you apply a force on the sand, when I put a leg on the sand, what happens? It will try to increase its shear rate here. Okay, are you following what exactly I'm trying to say? It will try to increase its shear, means it will try to change its shape here. Fine. Same thing if you take a ketchup. Ketchup, if I pour the ketchup, what happens? It will try to change its shape or increase its shear rate here. Okay. So that is what the pseudo-plastic fluid it says here. Okay, whose viscosity or consistently decreases. Okay, with an increase in shear rate here. Then what is Newtonian fluid? So Newtonian fluid which obeys, okay, or the shear stress is directly proportional to the strain which obeys the law is called as Newtonian fluid here. Okay, or which obeys Newton's law of viscosity is called as Newtonian fluids. Yesterday we have seen that is shear stress is directly proportional to strain. Okay, so for a Newtonian fluid, viscosity is entirely depend upon what? The temperature and pressure of the fluid here. Example like water, air, emulsions. So these are called as something about the Newtonian fluids here. Your blood. So blood is also something about it comes under Newtonian fluid here. Okay. Then what is non-Newtonian fluid? So it does not obey Newton's law of viscosity. Okay. So when I have to apply more stress, so more stress I have to apply. Okay. Then example, you can see the flubber or any like a grease type of structure. Okay. Then paste, gel or polymer solutions. Okay. So these are called as something about Newtonian fluid. So starch in water, then your gel, okay, then your toothpaste. So this are all comes under non-Newtonian fluid which does not obey the Newton's law of viscosity. Okay. So here what happens? Shear stress is not directly proportional to the shear strain or strain, or stress is not directly proportional to strain here. That is what non-Newtonian fluids talks about. So this is the graph indicates how exactly the variation in graph regarding with respect to velocity gradient and shear stress. So ideal fluid, I told you, it is like horizontal line. There is no such fluid exists. Okay, so it will be like no change in velocity means it will be a straight line. Okay, then Newtonian fluid. Okay, so velocity gradient will be there. Then when I apply shear stress, so you can see the figure. So when I apply a shear stress, what happens? Newtonian fluid goes on increases with the change in velocity gradient. But whereas non-Newtonian fluid, suppose for example I told you the paints or gel or toothpaste. Okay, so certain stage it will try to undergo stress. A certain stage it will try to undergo velocity gradient. Then almost it will try to decrease. So you can see the curve up to one stage it will be a straight line, then curve try to bend here. Okay, so that is called as something about non-Newtonian fluid. Then ideal plastic fluid or pseudo plastic fluid. Okay, so that is what it will be, a straight line. Okay, because otherwise, because again it will be talks about that emulsion means more like stress I have to apply. Then one is called as ideal fluid here. Okay, so this is the difference between ideal fluid, real fluid, Newtonian fluid, and non-Newtonian fluid or pseudo-plastic fluid here. Next, we'll talk about the thermodynamic properties of fluids here. Quickly, already we have studied in basic thermodynamics. Okay, quickly we will try to recall what are the different gas relations that comes under this fluid here. So how we learnt in gas relations in case of the thermodynamics, or we are going to learn in applied thermodynamics also. Same thing here also, we are going to learn the gas relation or the relation of the gases in properties of fluid here. So fluid, there are two types, one is liquid and one is gases. Gases can be compressible, whereas liquid cannot be compressible. So gases are compressible fluid which changes with respect to pressure and temperature. Okay. Then when it goes on changes, what happens? Gas undergo large variation in density. But whereas in liquids, there is not much variation in density will be there. Okay, I told you, because density of almost all fluids, it remains constant. Okay, not much variation will be there when it is undergoes the pressure and temperature. But whereas in gases, there is much variation will be there regarding the density in gases here. So PV is equal to RT, normal relation we have seen. So again I can write the V can be written as, okay, it is 1 by rho. Okay, so V can be written as 1 by rho. What is 1 by rho? Again, it is a reciprocal of density. Okay, so therefore P by rho is equal to RT here. So that is what relation that comes in fluid mechanics. So normally we have seen relation PV is equal to RT in almost all thermodynamics, but density comes into picture. That is what the equation talks about. P by rho is equal to RT here. Fine. So R relation talks about, what is R relation? Previous equation, that is, if I go previous equation, P by rho is equal to RT. From that, what is R? R is equal to P by rho T, that is P, it is in Newton per meter square, then density is kg per meter cube, then T is Kelvin, then meter gets cancelled, then Newton meter per kg Kelvin, or 1 Newton meter can be written as 1 joule, okay, then kg Kelvin. Therefore R can be written as joule per kg Kelvin, or 29.3 for air. The molecular weight of the oxygen or the air can be written as, the value is 29.3, or almost all oxygen molecular weight is something about 29 into, that is 9.81, okay, into acceleration we have to add it. So therefore almost all we are getting R value as 287 joule per kg Kelvin. So this is just I am discussing about what are the units that will come, or what is the relation of R here. So there are two processes will be there here. One is isothermal process, one is adiabatic process. Okay, in fluid mechanics also we are going to learn two processes. Isothermal means temperature remains constant. So therefore P by rho is equal to constant. So for adiabatic, no heat exchanges to or from the gas. No heat exit out of the system, no exit into the system here. That is P by rho raised to K is equal to constant, where K is a ratio of specific heat. How we have seen in BTD Cp by Cv. Therefore, same thing it will come here. K is equal to 1.4 here. Okay. Then, in fluid mechanics, there is one more property called as bulk modulus and compressibility. Okay. What do you mean by this bulk modulus? Okay. So bulk modulus is one in which where exactly we can use this. Okay. So bulk modulus is used to measure how incompressible a solid is. What is the strength of particular fluid or particular solid? Okay. How incompressible a solid is. How far I can compress the fluid here. Okay. The more the value of K, bulk modulus can be denoted as K here. So the more the value of bulk modulus for a material, the higher is its nature to be incompressible. So the more the value of K, that is bulk modulus for a material, the higher is its nature to be incompressible. Suppose, for example, not to understand clearly, suppose K for steel, bulk modulus of steel is 1.6 10 raised to 11 Newton per meter square. This is the highest value for a steel. Same thing if you take a glass, 4 into 10 raised to 10 Newton per meter square. Means the more the value of K for a material, the higher is its nature to be incompressible. That is what it measures, how incompressible a solid is. That is what bulk modulus it talks about. Okay. Then on the other hand, what is compressibility? How it can be related? It is a measure of the volume change of fluid or solid as a response to its pressure change. When there is a small change in pressure, it will means there is a volume change of fluid will be there. So what happens when volume increases? So pressure decreases. When pressure increases, then volume gets decreases. So compressibility talks about, okay, that is volumetric strain or volumetric strain to the compressive strain. So volume divided by compressive, it talks about the compressibility. Volumetric strain divided by compressive stress is called as something about bulk modulus, compressibility. Something bulk modulus talks about, what is the definition? Compressive stress divided by volumetric strain. So both are reverse here. If bulk modulus definition says compressive stress to volumetric strain, reverse of that is compressibility. That is volumetric strain divided by compressive stress. So both are interrelated here. Okay. How it can be interrelated? Okay. A substance, what happens, that is difficult to compress has large bulk modulus. We know that one. A substance which is difficult to compress has large bulk modulus. But what happens? But smaller the compressibility. Okay. So what happens? Compressibility will become small here. I'll repeat. How exactly we can relate the bulk modulus and compressibility means a substance that is difficult to compress has large bulk modulus. When I take a substance, it is difficult to compress when it is having a large bulk modulus. But when it is having large bulk modulus, the compressibility will be small. That is how the compressibility and what? The bulk modulus are interrelated here. Fine? So large bulk modulus when it is difficult to compress, but smaller the compressibility. Okay. So now to understand more clearly, then how exactly I will talk about in coming slides. So I told you bulk modulus is compressive stress to what? Volumetric strain. That is the definition of bulk modulus. Okay. So again I'll repeat. Bulk modulus, what is the use? How far the compressibility of a solid is. How far the fluid is compressed. Okay, that is what it talks about bulk modulus. Then it is the ratio of compressive stress to volumetric strain. So provides information about resistance of substance to uniform pressure. When it is subjected to uniform pressure, so provides information about resistance of a substance. How far it will resist the substance here. So it talks about compressibility of the substance. Whatever the substance that is there, it talks about the compressibility. How far the compressibility is. I told you. So when it is difficult to compress a substance and it is having large bulk modulus, but what happens to compressibility will become very small here. Okay. So higher the, suppose if I take a substance, higher the compressibility, if I take any substance, higher the compressibility, the value of bulk modulus will be low here. Higher the compressibility, okay, what happens? The bulk modulus will be low here. So lesser the compressibility, the bulk modulus will be higher here. That is what it relates the bulk modulus here. Okay. So compressibility and bulk modulus. So again, compressibility can be defined. It is the reciprocal of bulk modulus. Okay. Again, bulk modulus can be defined as compressive stress to the volumetric strain. How exactly it can be interrelated by taking a small figure here. So let us take a piston and cylinder arrangement. Okay. Then where P is the pressure acting on the piston, where V is the volume, capital V is the volume. Okay. Then dV is a small change in volume. Okay. So when pressure is applied, when pressure increases, what happens? Volume gets decreases. So dV indicates decrease in volume. Okay. dP indicates increase in volume. Okay. So I told you, the more the higher the compressibility, okay, or whatever the difficult, or a substance that is difficult to compress, a large bulk modulus, okay, but there is a small variation in compressibility, same thing. So let V be the volume of gas enclosed, let P is the pressure of the gas, let P plus dP is the increase in pressure, where V minus dV is decrease in pressure, where dP is increase in pressure and dV is decrease in volume. Therefore, volumetric strain can be defined as, or it can be related as, that is minus dV by V here. So why minus dV by V means when there is an increase in pressure, okay, when there is an increase in pressure, volume gets decreases. That is what minus dV by V it says. Therefore, bulk modulus can be defined as increase in pressure to the volumetric strain, or compressive, okay, strain, or compressive stress to volumetric strain here. Therefore, K can be defined as, that is increase in pressure can be called as dP by minus dV by V, or minus dP V by dV. Okay. Or compressibility on the other hand, beta is equal to, so it is the definition it says, that is reciprocal of bulk modulus, or minus dV by V by dP, or beta is equal to minus dV by V dP. That is how the compressibility and the bulk modulus are the interrelated in case of fluid mechanics. Okay, the higher the compressibility, okay, the lower the bulk modulus. The lesser the compressibility, higher the bulk modulus. Therefore, this is how the compressibility and bulk modulus are related here. Okay, fine. So let us understand what is the surface tension and capillarity. The next property of fluid is surface tension and capillarity. Surface tension, it is denoted as sigma. So what happens in surface? What do you mean by surface tension? It is a phenomena, or it is when it's very exactly the tensile force acting on the surface of the liquid in contact with gas. Tensile force acting on surface of the liquid, okay, in contact with gas, or on the surface between two immiscible liquids, such that the contact surface behaves like a membrane under tension. So under tension, what happens? Okay, under tension, so whatever on the surface of the liquid, okay, when it is in contact with gas, okay, it behaves like a membrane here. It behaves like a membrane, or tensile force acting on the surface of liquid in contact with gas, or on the surface between two immiscible liquids, so that the contact surface behaves like a membrane under tension, is called as something about surface tension. Or surface tension, it is denoted as Newton per meter. If you see this figure, okay, then there are different liquids are there here, different molecules of the liquid. So there is a tension is created here. Fine. Tension is created on the fluid element or on the molecule. So either upward direction or right hand side direction or downward direction, in different direction, the fluid or on the molecule, it will try to create a tension. Then when it moves in upward direction, okay, on the surface, it behaves like a membrane. Okay, that is what the concept behind this surface tension. Okay, in clear cut idea, if I show you the figure, okay, if A is the molecule and B is another molecule and C is another molecule, so on A element or on A molecule, different what happens? The forces or different tension is created. Then B, if you see, okay, partly, okay, it is on the surface, and C is almost all, it is behaves like a membrane here. Okay, so that is what under tension, okay, on the surface it behaves like a membrane. That is what it can be called as surface tension. So we are going to deal the three cases here: surface tension on liquid droplet, surface tension on hollow bubble, and surface tension on liquid jet. So we are going to learn the three cases. Okay, three cases of the surface tension on droplet, bubble, and jet. Then we shall understand how exactly the analysis on the droplet, bubble, and jet goes by proving with some relation here. Okay, so surface tension on liquid droplet. Okay, if you see this figure, three figures. First figure it says it is liquid droplet, and second figure it says when the liquid gets half, two halves, or when it is divided under the surface tension sigma. Okay, second figure. And the third figure it says that the pressure is applied. Okay, under surface tension when the pressure is acting on the fluid surface. Okay, then let R be the radius, and sigma is the surface tension of liquid, and P is the pressure intensity inside the droplet, and D is the diameter of the droplet. So from figure 2, so tensile force due to surface tension can be written as sigma into circumference, or sigma into pi d here. So pressure forces, this is tensile forces over, then pressure forces, that is pi by 4 d square is equal to P into pi by 4 d square. Okay, that is pressure forces into pi by 4 d square. From figure 3, if you see pressure forces for figure 3, if I write, that is pressure into area, that is pressure into pi by 4 d square, or pressure into pi by 4 d square into, if you relate the equation, into sigma into pi d, then pressure is equal to, you can write it as 4 sigma by d here. So what is that relation it talks about? So decrease in area, it is 1 by d, decrease in diameter of the droplet. When there is a decrease in diameter of the droplet, pressure intensity inside the droplet goes on, increases. That is what the relation it talks about. Okay, so decrease in diameter of the droplet, okay, pressure intensity inside the liquid droplet goes on, increases. That is what the relation it talks about. Same thing for hollow bubble. Hollow bubble, in a sense, example, if I take a soap bubble in the air, when you just blow, when you dip the soap water and when you blow through a small pipe straw, so when it flows in the air, that is called as a hollow bubble. Okay, otherwise it can be called a soap bubble. So again, soap bubble can be written as same relation, that is pressure into area. That is because it is an hollow. Okay, so 2 times of circumference into area it will come. Okay, hollow bubble it is there. So 2 times of circumference into diameter, that is area. That is pressure can be written as, that is 8 sigma divided by T. Same thing, this relation, decrease in the diameter increases the pressure intensity inside the droplet. Okay. Same thing for jet, liquid jet. If L is the length of the first figure, if L is the length of the liquid jet, and if sigma is the tensile force, okay, that is when it divides the fluid. Okay, so tensile force will be acting. So force due to pressure, pressure into area of semi-jet, that is pressure into L into D. Force due to surface tension, that is sigma into 2L. Okay, that is, if I equate the term, P is equal to sigma into 2L divided by length into diameter. Same thing here also. When there is a decrease in diameter, when there is a decrease in diameter of the droplet, the pressure intensity goes on, increases in particular droplet here. Fine. Then the next property is called as capillarity. What do you mean by capillarity here? Okay. So capillarity means there is a rise or fall of liquid surface in small tube. There is a rise or fall of liquid surface in a small tube relative to the adjacent general level of the liquid. Okay. When tube is held vertical in the liquid, it is called as something about capillarity. If you see this figure, okay, the first figure, when there is a water or when there is a mercury, when there is a water, there is the fluid rises. There is a lift in the fluid, or the fluid it rises here in the tube. Okay, when I talk about this, the fluid rises when I take a water. Okay, the vertical tube will be there. Then through that vertical tube, the water rises here. This is called as something about capillary rise or the rise. Okay. Same one more figure if I see here, if I provide mercury, another fluid, okay, the rise in fluid may not be there here. Okay. No rise in fluid. In water we have seen there is a rise in fluid, but here in mercury the fluid doesn't rises through the vertical tube. That is called as a fall here or capillary depression. So altogether it is a phenomena rise or fall of a liquid surface in small tube relative to adjacent general level. What is that adjacent level? The mark of beaker. Okay, the level of the beaker. So adjacent general level of the liquid. When tube is held vertical in the liquid is called as capillary or capillarity. So two types will be there. One is capillary rise and one is capillary fall. In another way of explanation, okay, so mercury doesn't rises through the tube, but whereas water rises because there is an attraction. Okay, in water the attraction will be more, so water level rises here. Okay, the simple example I can give here is tissue paper absorbing ink due to capillary action. When you take a dip the tissue paper in any water, it will try to suck very quickly here because there is a capillary action will be there. But whereas if you place a mercury, it does not absorb. Okay, that is called as a rise or fall here. Okay. Then there is expression we have to learn here. Expression for capillary rise. Okay, what is that expression it talks about? Let me understand clearly through the figure. So what is capillary rise it talks about? Okay. If h is the height from the level of the liquid to the that is raised in the tube. Okay. If h is the height of the tube up to the level in the tube here. Okay. Height of the surface in the beaker to the fluid that has been raised in the vertical tube. Then if sigma is the tensile or surface tension, then if theta is the angle between the tube and the upper portion of the tube, okay, and whatever the rise that is there here, so theta is the angle between the surface, okay, then the parameters, what exactly it will come, if d is the diameter of the glass tube, if h is the height of the liquid in the tube, and sigma is the surface tension, and theta is the angle between, I told you, the liquid and the glass tube. Okay. Then the weight of the liquid of height h in the tube can be written as, the weight of the liquid of height h in the tube can be written as, that is A is the area of the tube, okay, h is the height of the fluid, and rho is the density of the fluid, and g is the acceleration due to gravity. Therefore, A is pi by 4 d square into h into rho into g here. So vertical component of surface tensile force, vertical component, that is sigma into circumference into cos theta. Okay. Previously we have written that is weight of the liquid, height h in the tube. But here in second expression we have to write vertical component of surface tensile force, that is sigma into circumference into cos theta, or sigma into pi d into cos theta. Equation 1 and 2 equating. So finally the equation can be written as h is equal to 4 sigma cos theta divided by rho into g into d. Here cos theta will become almost all it is small. Okay. For a liquid, it is the angle between the liquid surface and the tube. So it will become very small here. It can be written as unity here. Okay. Small value in essence, it can be written as unity, that is theta is equal to 1. Okay. So therefore, the equation can be written as h is equal to 4 sigma by rho g d here. Okay. 4 sigma by rho g d. This is what the relations of the capillary rise. Same thing, capillary fall. Okay. If I take this figure, the red color strip, it is, if I provide mercury, there is not much rise in the fluid, there is always a fall. The pressure P is the pressure intensity acting on that fluid. Okay, it will try to rise inside the vertical tube, that is pressure intensity P. If sigma is the tensor, that is surface tension. If theta is the liquid between the surface of the tube and the liquid. Okay, if h is the depression, here h will become depression. In previous slide we have seen h gets increased here. H is increased, but here h is depression. Okay, it gets decreased here. So therefore, there is a upward direction, there is a forward direction, because pressure intensity will be acting on the fluid on the upward direction, or the air will be acting on the downward direction. So here, this is what the case you need to understand. The first force downward direction, that is sigma into pi d into cos theta. Okay. Then means upward, that is from top to the bottom, the forces that is acting. Okay. Sigma into pi d into cos theta. Then second force is the upward, from bottom to up. Okay, upward direction, that is h into area of the tube. That is, if I write, therefore if I equate, that is P into, P can be written as, the pressure can be written as here, the density of the fluid, that is rho GH. P can be written as rho GH here. That is, substitute that P value here, that is P rho GH. Okay. That is P into pi by 4 d square. Okay. That is, P can be written as P into pi by 4 d square. That is, P can be written as rho GH into pi by 4 d square. That you can call as equation 1. So equating above equation, first equation and second equation. So therefore h can be written as 4 sigma cos theta divided by rho g d. Here, whatever the angle, because angle variation is higher here, so it is a designed value, therefore theta can be written as, it is measured angle 128 degrees. But in previous capillary rise, there we have taken, because it is a small variation will be there, almost all it is 1 degree or 2 degree. Okay, there we have taken cos theta as 1 in capillary rise, but here it is a measured value, that is 128. Therefore substitute that value to get a required h here. Fine. Thank you, students, for your attention for today's class. Okay, so tomorrow we are going to learn the brief about the problems. Simple problems I'll try to solve in tomorrow's class here. Thank you, students. Thank you for your attention. Okay, so we'll meet again on Monday here. Thank you.